We've observed a new particle. We have quite strong evidence that there's something there. So to ascertain its properties is still going to take us a little bit of time. On the other hand, we see that it decays to 2 photons, for example, which tells us it's a boson. It's a particle with integer spin, and we know its mass is roughly 130 times the mass of the proton. And this is very significant. This is the most massive such particle that exists, if we confirm all of this, which I think we will. And that is very, very significant. This is something that may, in the end, be one of the biggest discoveries or observations of any new phenomena that we've had in our field in the last 30 or 40 years, going way, way back to the discovery of quarks, for example. We see very strong, very, very strong evidence in the decay to 2 photons and a very, very narrow peak in our distribution. We see also evidence for the decay to 2 Z particles, which are like heavy photons in a particular theory of elementary particle physics. And then we've studied a number of other channels that are reported. But these are less sensitive, and the results are less conclusive at the moment. But we're very excited. I'm extremely tired at the moment, so I may not appear to be as excited as I really am. But the significance of this observation could be very, very great. It could be ultimately seen that its properties are very consistent with the Standard Model Higgs. Or we may find out that some of its properties don't exactly match the expectations for the Standard Model Higgs. And if that's the case, then we have something really quite profound here. And it could be a gateway, if you like, to the next phase of exploring the deepest parts of the fabric of our universe, which is pretty profound when you think about it. And the other thing I would like to say is that obviously all of this is extremely preliminary. What we look for is a few grains of sand on a beach, in some sense. I did a calculation, and if you replaced every event, every collision of the beams that we've scanned or had take place in our experiment over the last 2 years, if you let each one of those be represented by a grain of sand, you'd have enough sand to fill an Olympic-sized swimming pool. And the number of events that we've collected now that we claim represent this observation are of the order of tens or dozens. So it's an incredibly difficult task, and it takes a lot of care and cross-checking. We're recalibrating, and we'll have better results, even on the current data, by the time we publish at the end of this month. But it's certainly very exciting. When we say we've observed the particle, it means we've just got enough data to say it's definitely there, and it's very unlikely to go away. Okay? That's what an observation is. We then need more data to start to ascertain its characteristics. What are its properties? Can we really ascertain exactly what spin it is? We know it's an integer spin. It's an even integer spin. There are other properties like parity, its exact value of its mass. What other decays does it have? All of these things tell us the nature of this thing. It's actually, if it were the Higgs boson, for example, then it would have a big array of possible decay modes that we have to study. It may be something which we often call a Higgs-like particle, or a Standard Model Higgs-like particle, but not Standard Model. And by studying all of these different characteristics, we can begin to say whether it is or is not. Now, actually, it's extremely hard to say it is, because there are many models that predict a boson that has more or less the same properties as the Standard Model Higgs boson. But if it doesn't match, okay, in a significant way, we may be able to find that out, and we may even be able to find that out this year. And if that's the case, well, then that's a major, major thing. This is a revolution, in fact, because we have the possibility then, studying this thing and seeing how it's different from what we would have expected for a Standard Model boson, we get some clues about what else is out there. And it really could be a portal to almost an entirely new dimension, if you like, a dimension of new particles, as in supersymmetry, literally new dimensions to the universe, new spatial dimensions. These details may be hidden somewhere there. Whether or not we can extract that much is unlikely in the next year or two, but we'll have hints of that perhaps. So the data we gather the rest of this year is really, really important. And then, of course, we need to continue running in future years. We'll go to higher energy, which will actually help a lot. And there's always the possibility now that there are other particles. It's a very good possibility there are other particles to be found. So this is very exciting. Well, in my career, we've had only a couple of really major discoveries in the field. When I was very young, there was the W and Z particles that were discovered, which are part of the same theory that created the hypothesis of electroweak symmetry breaking and the Higgs boson. It was the discovery of the top quark. We knew it had to be there, but it turned out to be much more massive than anyone expected. And that happened in the 90s. And since then, we haven't had really major discoveries. But this one, I mean, this is a fundamental boson, if you like, a particle with possibly no spin. It could be a fundamental particle. It's very heavy, much heavier than any other particle we know except for the top quark. And that is something that was predicted. And if it corresponds to those predictions in any of the possible guises that exist in the various theories, then we're really seeing something very, very closely tied to the fabric of space and time, something that's really fundamental to the universe. And that represents a major discovery, and perhaps as big as the discovery of quarks, perhaps as big as the discovery of antimatter. So going back, well back into the last century before you find something that big in our field is possible. Of course, we have still work to do to confirm all of these things. But we think this is pretty darn significant.